Okay. We will discuss a system of linear equations in n unknowns x1, x2, xn. In this system, is written in this fashion. The first equation is written as a11x1 plus a12x2 plus a1n xn equal to b1. Second equation is written as a21x1 plus a22x2 plus a2n xn equal to b2, and so on. And finally, we write the mth equation in the same fashion. This notation is used so that we can write this system of m equations in n unknowns in matrix form, and we extract the coefficients a, j, k of this system of linear equations and record them in a matrix A, which is m by n, and let x be the column vector of unknowns x1 up to xn, and b is the column vector of known quantities b1 up to bm, and the equation, the system of linear equations, amounts to writing the matrix equation Ax equal to B. So m equations in n unknowns can be written in very compact form as Ax equal to B. The matrix A is called the coefficient matrix, and a vector C with n components is called a solution of Ax equal to B if AC equal to B. If B equal to 0, then Ax equal to 0. This is called a homogeneous linear system, and the homogeneous linear system has a zero solution because A times 0 is 0. You can check by using matrix multiplication that A times 0 is the 0 vector, and therefore homogeneous linear systems are always consistent. A general solution Ax equal to B may not be consistent. Now, if C1, CR are solutions of Ax equal to 0, then we can take a linear combination alpha 1 C1 plus alpha R CR. And this is also a solution of the same system of equations, homogeneous system of linear equations, because A times alpha 1 C1 plus alpha R CR by properties of matrix multiplication and linear combinations, it is equal to alpha 1 AC1 plus alpha R ACR, and that is equal to 0. A general linear system has B as an arbitrary vector, and this is called a non-homogeneous system if B is not equal to 0. Now, a non-homogeneous system may have no solution, one solution, or infinitely many solutions. This linear system, x1 plus x2 equal to 1 and 2x1 plus 2x2 equal to 1, doesn't have a solution because these two linear equations actually represent two lines, and these are parallel lines because their slopes are equal. So two systems, two linear equations in two unknowns may have no solution. But look at the equations x1 plus x2 equal to 1 and x1 minus x2 equal to 0. This has a unique solution. These are two lines in the plane and they're intersecting in a unique point, namely half comma half. So these two equations in two unknowns have a unique solution, and it is a non-homogeneous system of equations. Yeah. Now we can write down a general system, the general solution of x1 plus x2 equal to 1 and 2x1 plus 2x equal to 2 in terms of real numbers. These two equations have infinitely many solutions because geometrically these are exactly the same line. So these two lines coincide, and therefore we expect infinitely many solutions, and we can write down the infinitely many solutions by substituting arbitrary value of x1 equal to alpha, and then x2 becomes 1 minus alpha, and therefore there are infinitely many solutions. So just this simple case of two unknowns and two linear equations tells us three possibilities for solutions: no solution, or one solution, or infinitely many solutions. There are no other cases of solutions of systems of linear equations. We will soon prove this fact for arbitrary system of linear equations, that either there is no solution, or there is a unique solution, or there are infinitely many solutions. So we want to now break up the problem of solving system of linear equations into two parts. First, you look at the homogeneous system of linear equations Ax equal to 0. And by some means, suppose we know the set of all solutions. So let S be the set of all solutions of Ax equal to 0. and our system of linear equation is Ax equal to B, we find one solution of Ax equal to B. One solution of Ax equal to B is called a particular solution. Then the set of all solutions of the general system Ax equal to B is obtained by adding all the solutions of Ax equal to 0 with the particular vector C. So add C to each and every solution of Ax equal to 0, then the resulting set of vectors is the set of all solutions of Ax equal to B. Let us prove this fact. So let us pick an element C plus S, where S is one solution of Ax equal to 0 and C is a solution of Ax equal to B. Then A times C plus S is AC plus AS. AC is equal to B because C is a solution of Ax equal to B, and AS equal to 0 because S is a solution of Ax equal to 0. And therefore, A times C plus S is B, and that shows that C plus S is a solution of Ax equal to B. Now we prove the converse. We want to show that every solution of Ax equal to B looks like C plus S, where S is a solution of Ax equal to 0. So suppose we subtract the vector C, which is a particular solution, from an arbitrary solution of Ax equal to B. So look at A times X minus C, that is Ax minus AC. This is B minus B, this is 0. And therefore, X minus C, whenever X is a solution of X equal to B, X minus C is a solution of the homogeneous system, and therefore X minus C must belong to the set S, and therefore X is equal to C plus S for some S in this set S. So this shows that the set consisting of C plus S, where S is varying over the set S, is the set of all solutions of the general system of linear equations Ax equal to B. Therefore, the problem of computing all solutions of a system of linear equations is broken into two sub-problems. The first problem is to write down all solutions of the corresponding homogeneous system Ax equal to 0. The second problem is to find one particular solution of Ax equal to B, and then suppose C is that particular solution, we can translate all the vectors in the set S by this fixed vector C to get all solutions of Ax equal to B. So let us now discuss a particular case of system of linear equations. We will see that this particular case gives us enough experience to tackle the general case. So in this particular case, the coefficient matrix is upper triangular and its diagonal elements are non-zero. So we have n equations in n unknowns. The first equation have all the variables x1 up to xn. The second equation doesn't have x1 in it. The third equation will not have x1, x2, x in it, and so on. The last equation has only one variable xn. So as we move down, one variable disappears from the equation at a time. And finally, the last equation has one variable only, a and xn. And we are assuming that the coefficient matrix is upper triangular and the diagonal entries are non-zero. And therefore, we start with the last equation, a n n xn equal to bn, and we can solve for xn. And xn is uniquely determined from the last equation. Then we go back and substitute xn in the n minus first equation, and that says that xn minus 1 is uniquely determined. Then substitute xn and xn minus 1 in the n minus second equation, and that will say that xn minus 2 is uniquely determined in terms of xn and xn minus 1, and so on. And finally, x2 is uniquely determined from the second equation, and go back and substitute in the first equation, and we can get value of x1. So this system of n equations in n unknowns, where the coefficient matrix is upper triangular and diagonal entries are non-zero, has a unique solution. And we now look at a general system of linear equations and try to convert this into a system which is similar to this. Okay. Now, if you have a homogeneous system Ax equal to 0, that has only the 0 solution. Therefore, it is a consistent system. And so the set S in this case consists of a singleton, namely the 0 vector. And so if Ax equal to B has a solution, then it will say that this has a unique solution. Yeah. because all solutions of Ax equal to B are obtained by simply translating one solution by each and every solution of Ax equal to 0. But if Ax equal to 0 has only the 0 solution, then Ax equal to B will have a unique solution. Now we take Q from this special case of an upper triangular matrix, and we will transform any M by N matrix into an upper triangular form and use this method of back substitution to arrive at a solution of a general system of equations. So above process can be carried out without writing down the entire linear system. We simply look at the what is called the augmented matrix. The augmented matrix is obtained by simply adding the B vector as a last column to the coefficient matrix, and the first row will be the first row of A along with B1. The second row is the second row of A along with B2, and so on. So we construct this augmented matrix. So the entire information about the system of linear equation is contained in this augmented matrix. We will now try to modify the augmented matrix by what are called row operations. And these row operations are not going to change the set of solutions. They will change the system of linear equations, but they will not change the set of solutions. Using the row operations, we try to simplify the augmented matrix so that at the end, it becomes a upper triangular matrix. And once we have an upper triangular matrix, then the corresponding system of linear equations can be solved by the backward substitution process.